starting our unit on waves, and this is a little introduction to waves. So this kind of page in your notes, I think it's like 23, talks about all different types of waves. So all types of waves have these sorts of properties or ideas. And I'm sure you have some background information on waves. So this is kind of nice because if you know some of these things, you can kind of fast forward or put me on high speed. Um, so in your notes, we're thinking about waves. So what does a wave do? The key idea behind a wave is that it transfers energy. That's the big idea. So a lot of the times we call it a vibratory or oscillating disturbance that transfers energy without transferring mass. So just the energy is moving, no mass. And I'm realizing this is kind of cut off. So a wave is a vibratory disturbance that transfers energy without transferring mass. So my favorite example of a wave is the stadium wave. So in a football stadium or in a soccer stadium or any sort of stadium, you have a time on occasion where people will stand up and raise their arms up, and then the next person stands up and raises their arms up, and the energy is transferred from person to person to person through the stadium faster, usually, than any one person could really walk around the stadium. And so this is one example that's a really nice example of a wave and showing this idea that the energy moves from molecule to molecule or person to person without actually the matter moving or the person moving. So energy is being transferred, but the mass is kind of not moving. So a stadium wave is one great example. An ocean wave is another great example. If water was actually being moved from, the Atlantic, from England over here to New York, then actual physical water, then the ocean would be empty, right? So it's just the energy that moves through the waves. Actual molecules or matter don't move. Sound waves are another great example. Microwaves, which are a little harder to think about, along with light waves, are also types of waves, and we'll call those electromagnetic waves. So a single crest or pulse or energy disturbance moving through a medium is called a pulse. And you can think of waves, we'll draw them a lot of the time in this way, almost like a sine curve in trigonometry. So we start out kind of with a 0-degree phase, if you will, and then 90 degrees, 180, 270, 360. So that's one full cycle here, and I've drawn two complete cycles here. So the peak, which is at 90 degrees in this case, is up here. There's two peaks drawn, or crests, and then there's two valleys, or sometimes they're called troughs. You also might call these maxes or minimums. And so these waves can travel through all sorts of stuff, and what we call the material that a wave travels through is something called a medium. So I'm talking to you right now through air. So the sound wave is traveling and the energy is moving through the air. So the medium in this case is the air. With a stadium wave, the medium is actually the people. With an ocean wave, the medium is the water. And then we'll talk a little bit about microwaves and light waves. They actually don't operate with a medium at all. So a mechanical wave is a wave that requires a medium to travel. And another fancy word we're going to see for travel is propagate. So a mechanical wave requires a medium to travel, but then there are these other types of waves that are called electromagnetic waves that do not require a medium whatsoever. So electromagnetic waves are broadly defined as all of the various wavelengths and frequencies of what we might call light. So there's radio waves, there's gamma rays, there's X-rays, there's microwaves, there's UV rays, infrared, visible light, and I think I named them all. There's 7. So taking a step back, there's a lot of different types of waves they all transfer energy, we can break them into two categories: a mechanical wave that has a physical medium through which the energy travels from, say, molecule to molecule, and then there's electromagnetic waves which do not require a medium. So a really great piece of evidence for the fact that electromagnetic waves do not require a medium is the fact that we can see the sun. And it seems so obvious, but the sun produces light, which is a type of electromagnetic wave, and the light that is produced from the sun travels through the vacuum of space. So there is nothing in space, essentially. Sometimes there's a molecule every once in a while, but the word vacuum means that there's nothing there. So it travels through the vacuum of space and it reaches us. So light is an electromagnetic wave, and the sun produces light and it travels through nothing, basically, and comes to us. So light is a really weird thing, and we're just going to kind of table light for a second as we think about physical waves like sound, which is the movement of energy from molecule to molecule through the air or through any medium, really, through water, through steel, or through the table. So sound cannot travel in space, though, and so a lot of movies depict like these huge explosions in space, and a couple of them have more recently have done really good jobs. I think the most recent Star Wars did a really good job showing an explosion with dead silence, because that is really what it would be, because there's no molecules for the sound energy to transfer through in space. So there's two different categories of wave motion we're going to think about. One is called transverse wave motion, and trans means kind of like opposite. So in this case, the wave travels in one direction, so it propagates, again, that fancy word for travel. The energy moves in this direction, but the particles move up and down. So a transverse wave is a wave in which particles move perpendicular to the direction, or kind of opposite to the direction of propagation. An electromagnetic wave would be a great example of that, and a stadium wave, so that those people standing up and coming down, they're going up, but the energy is traveling side to side. I have a simulation with a transverse wave as well. So I can shake this this wrench, or I can make it oscillate. I'm going to turn the damping down so there's no damping, and I'm going to make it no end so there's no interference. So we just have these particles moving up and down. I'll pop it into slow motion, and the energy traveling side to side. So the energy travels towards the right of the screen, but the particles move up and down. So this is a transverse wave. Now, a longitudinal wave is this next type of wave, and a longitudinal wave is one where the particles actually move in the same direction as the energy transfer. So this is like our sound wave. So you can imagine my voice over here, and I'm pushing molecules, giving them energy, compressing them. So there's this word compression and rarefaction, and then they're kind of spreading out, and we have something called a longitudinal wave. These are also called pressure waves, or even P waves from earth science. So we see these in a lot of different places. So back to the notes, a longitudinal wave or a pressure wave is a wave in which particles move in the same direction of the wave's propagation. So here's like our speaker, and the diaphragm of the speaker pushes on the molecules of air, and it creates these peaks and troughs, which are really compressions and decompressions, or a fancy word for that is rarefactions. So compressions and rarefactions of molecules. So these compressions are peaks, and the wave actually travels to the right, and the particle moves to the right and to the left. So sound waves are an example of this, and heat waves are an example. So that is it for just regular wave properties. Tune in next time.